So in today's microprocessors, microcontrollers, embedded systems lesson, we are going to be looking at communication, but communication mainly in the context of embedded systems, the type of communication that would be relevant when we are building embedded systems. For those who would have done other data communication, signaling, that type of modules previously or in parallel, many of the things would be fairly familiar. But here we are mainly looking at those in the context of how those communication techniques and technologies can be applied when we are building embedded systems. The reason why we are we need communication is that when we think about embedded systems, when we think about even real-time systems, some of them could be standalone devices or standalone systems. They could just do everything within the system itself, and that's all they do. But in many situations, we would ideally want to have systems that are connected to other things, that are connected for the purpose of controlling them, that are connected for the purpose of them providing us with some information, that are connected for the purpose of us providing some information into the system, and sometimes even connection between these systems so they can talk to each other. So this is something that we would expect in many different types of embedded systems. So for that reason, we would have to have some form of communication happening. And in the case of, say, for example, real-time systems, we would also have requirements, things like periodic or event triggered, so like either time triggered or event triggered tasks. So again, those may be communicating messages, those may be communicating updates, other signals. So there are various scenarios, various situations where we would be using messaging, or we would be using communication. One of the most interesting aspects of systems that we would come across are the type of systems that we could classify as distributed systems. So when we talk about distributed embedded systems or distributed real-time systems, this is when we have a number of these devices, and each of those devices are able to communicate with each other, and they can share information, they can share updates, they can share, communicate, and coordinate things within the systems themselves. So again, these are some of the type of systems that we would be talking about when we are talking about connected embedded systems, and the type of communication that we would need in such embedded systems. One of the other main situation or main scenario where we would need communication is to do with timing requirements, or is to make sure timing requirements of certain processes are met. And one of the ways these timing requirements can be ensured is that the various systems, the control systems, the actuators, the sensors, and all of these things are able to communicate, are able to pass on messages, and are able to act upon those messages received from other parties, so that all these tasks, all the processes can be coordinated in a from a in an organized manner. So that is again another requirement or another benefit that we would get by having communication between these embedded systems. And from an embedded system point of view, this is mainly about communication between sensors and actuators and control systems. But when we also do this with general computer system environments, where when we have multiple computers interconnected and they are doing things together, working sort of in sync, again they may need additional communication. So the general communication principles are the same across general computing or embedded systems, but with embedded systems we will have them used for certain scenarios, certain applications, and to gain certain advantages. So when we think about data communication, particularly in the context of control systems, particularly when we think about control systems, these are it can be embedded systems, they may not be embedded systems sometimes, but generally what we have in those scenarios is we will have plants or the actual control devices, then we will have sensors, we will have maybe other related controllers, and then we may also have other system managers and monitors. And when we talk about communication, we would have communication at all of these levels. If we take, for example, a HVAC system, a heating and ventilation system, there we would have when we say about plants, it could be the air conditioners and things like that, could be the air blowers, and all these things are the plants. The temperature sensors and humidity sensors, and these would be the sensors. We may have a number of controllers interconnected through a connected network, and then we may also have overall building management systems, building automation systems that are overseeing all these activities. So at that level, all of these things will have to communicate with each other and among themselves. So that is what we would expect in such an environment. So if we go back to the very basics of communication, this is something that you would be fairly familiar with. When we think about few entities needing to communicate with each other, there are a few ways that we can do that. One is called using a shared memory approach. So we have a shared memory where information can be, we can read and write information from different parties, and they can share information like that. So in a way, achieving some form of communication. Another approach is called using a bus approach. So we will have a shared communication bus through which all of these parties can share information. So they can send information, receive information, and so on. Then we have what are called point-to-point connections. With point-to-point connections, what we have is different entities are connected to each other, and they can communicate with each other through those connected links. And in some cases, they may also be able to pass through messages through those communication links. And the fourth category of communication is what we would identify as a shared medium communication. An example is the internet. So where every entity is connected to that common network, and then within that network they can communicate with each other. So these are switched networks, rather packet switch networks, and all of the entities connecting to the network are able to communicate with each other. But when we go above that simpler communication architecture, and when we think about the nature of communications that we may find in an organizational environment, the type of communication that we may find in a larger embedded system deployment, for example, we would have a variety of communication patterns, communication methods, and all of them working together. So we can have things like wireless communication. There can be internal or external wireless communication, cellular communications. We can have audio and video type of modules. They would be communicating, sharing information. We can have what are called CANs, or rather controller area networks. So these are sort of various communication networks that are mainly interconnecting controllers, sensors, actuators, and so on. So we may have different control area networks sometimes, and all of those interconnected through gateways. So we can have a much complex network architecture, distributed architecture, than the basic communication architectures, network architectures we may find. So in reality, we may have the nature of communication architectures that we have may be much more complex than the basic simple architectures. Then from an embedded systems point of view, from a communication perspective, one of the things that we would observe is the hierarchical nature of the need for communication. The type of communication and the nature of communication that will be needed and that will be done would have different purposes and between different types of devices at different levels. We can divide these into three main levels: device level or field level, control level, or information level, and or management level. So those are the three main levels that we can divide them into. And in device level, or we may also call it the field level, this is the type of communication that is happening between the sensors, the actuators that are available on the field. So the field level devices and the communication that is happening among those devices. Then the next level above is when we have the control level communication. So here is where we have the controllers, and it is possible for us to have a number of controllers, and they may be communicating with them, with each other. Then at a more higher level, we would have what is called information level or management level. So this is mainly about overall industrial automation systems, information gathering, information management, monitoring, that type of system. So that is the high level communication. But what we may observe with all these is we may have what are called various type of networks there are a number of these type of environment specific networks. We will look at some of these things like industrial Ethernet type of communication mechanisms. So these type of things will be available to interconnect all these things. So we may have these specific communication levels, and then we may interconnect between these levels using different communication methods. So those type of communication networks that we would have in industrial environments to interconnect these different levels. So to connect the field level devices to control level devices to operations level devices. So to do that, we may not use the standard general purpose computing networks. We may go with some specific industrial communication networks. There may be a number of reasons for doing that. For example, at a lower sensory level, sometimes using a typical IP-based communication may be inefficient in terms of the amount of information transfer and the requirements that we may have. So the type of devices, they may not have the capability in terms of processing power and so on to carry out a very high level communication network. So then what we may have in industrial environments is a variety of communication networks that are specifically designed for those purposes to interconnect the specific devices such as sensors, controllers, PLCs, these type of scenarios, these type of communication, these type of devices and communications between those devices is what we would get, we would try to achieve using specific industrial communication networks rather than general purpose communication networks. There are a variety of industrial communication networks, and they may be used for different purposes. Say, for example, we can use standards like serial communication standards like RS-232, or likewise, we can use those. That is possible, but we will have additional industrial networks like device net, control net, Profibus, foundation field bus. So these are some of the other industrial communication networks that we can specifically use when we are connecting embedded systems, when we are connecting controllers, field devices, various I/O devices. It may be possible for us to use some of these industrial communication standards because they will have much advantage in that particular application domain. Many of the devices that we may find will only support those communications. Like, say, for example, it may be easier to find sensors and controllers and things that support Profibus than them supporting IP-based communication. So different devices may support like sort of specific protocols, specific networks. So we may have to use them. And one of the things we may find with these different communication standards is sometimes we may have to have some gateways to interconnect between these, because we may have certain devices that are on device net and then certain others that are on a control net network, and then we may have to have some central gateway that is interconnecting between these different communication networks. So that may be a necessity as well. You can look up some more details of these from this link. So when we think about the general communication, that is the open systems interconnection or OSI layered architecture of communication, The main intention there is using them for computers. So hence most of the layered architecture and the use of the layers are for that purpose. So they serve the purpose of those computers, those applications. But because of that layered architecture, having many layers is also the reason why it becomes a complex communication mechanism, particularly in the case of many small size embedded communication requirements. So what we may come across is we may still use OSI based communications, we may use the same underlying infrastructure, but we would largely rely on the lowest level layers of OSI, the physical and data link layer, as the main use part in the embedded systems environment. And we may have other custom higher layers, or maybe not all the layers may be implemented depending on the requirement, but we may sometimes still use OSI based communication in embedded systems environment. So then when we think about embedded systems communications, the type of communications that we can have in embedded systems, we can sort of broadly categorize them into two categories as point-to-point networks and shared media networks. So again, this categorization is not specific to embedded systems. So any general communication systems we can categorize in the same way. And the communication systems that we would use in embedded systems also we can categorize into these. But because of the certain requirements that we may have in certain embedded systems, there may be a tendency to choose one or the other as the more suited communication method in those embedded system environments. So, for example, with point-to-point networks, what we have here is each of the nodes are interconnected with each other directly. So what we have is, say, if we have 4 nodes, each of the nodes are interconnected with each other directly. So there is a direct communication with each other. So then when we add a new node, now that node needs to be connected to every other node. So while we keep on adding more nodes, there is a requirement to interconnect them with all of the nodes. So in a way, it is a simple mechanism, because if this one needs to communicate with this node, there is a direct communication. So there is no additional midway through and all those things. It's a direct communication with any other node. So it is simple and it can be more reliable as well. Also, particularly with certain embedded systems and particularly with real-time systems, having such a dedicated communication link would be really useful, especially to meet real-time deadlines, because there's no other overhead, there's no other delays in communication, and we can have a much reliable, much suitable communication there. But one of the main disadvantages of this approach is it can be very costly, and when we have a significantly larger number of nodes, then the amount of interconnections that would be required will also increase with that. So in a way, it would be prohibitive for many reasons, including cost, size, and things like that. The other type of communication that we can have is using shared media networks. With shared media networks, what we have is essentially some form of bus infrastructure. So we may have a number of nodes, and these nodes may be interconnected using a bus infrastructure. So there may be a bus, and all of these will interconnect to the bus, and then that is how they are going to communicate. So there will be a shared medium. The bus is the shared medium that all of these are going to communicate through. So the bus will act as the shared medium. So comparatively, it is going to use less wires because now we don't have direct connections to each and every other node. It will be cheaper, again, for that same reason. And it can also be very easy when we want to expand the network and add new nodes. Say, for example, if you want to add a new node, we add a node and connect to the bus. Add a new node and connect to the bus. So, not a lot of overhead in adding new nodes to the network. But the main sort of disadvantage with this approach is now we need to have much more complex communication protocols. Because now, say for example, if this device needs to communicate that device, it has to go to the bus and then through the bus, then to the device. So it can be comparatively complex than doing just a direct communication. So that is the main sort of differentiation between point-to-point and shared media networks, and depending on our requirement, we may have to choose between one or the other in building our embedded systems. Then another way that we can categorize the communication, particularly in a more relevant sense to embedded systems, is based on what is called when the communication is happening. So there are event-based communication and state-based communication. So with event-based communication, what we do is when a certain event occurs, that is when we will be communicating. Say for example, if there is a user input, then it may be communicated. If there is an alarm or an error, or if there is some event happening, based on that, the communication will happen. On the other hand, when we talk about state-based communication, what we do here is at a regular interval, we will be communicating. So for example, if you want to get regular temperature sensor monitoring, so then every 1 minute, for example, we can send out the sensor reading through our communication. So here what we would have is sort of regular communications. So at certain time intervals we will be communicating that. So again, which way we want to communicate will depend on what we intend to communicate and the nature of that information. Say for example, if we are talking about user input, somebody pressing a button, somebody pressing a switch, so those things we can communicate when that event happens. But when we are monitoring something, when we are monitoring a sensor, then we can communicate that information on a periodic manner, on a regular manner. That is what we would call as state-based communication. So with event-based systems, we may tend to use event-based systems a lot more, particularly in low-powered embedded systems, because they would be efficiently using the network. Because we only need to communicate when there is a new information. If there is no new information, then we don't need to communicate. So it is fairly efficient in that manner. But because the information is only communicated once, or information is only communicated based on an event that happens, then we would need a fairly high reliability to do that communication, because here a particular event happens and then the information is sent out, and if that is not received, then there is no new information coming, because it is only sent once for a change of information. Say, for example, if you press a button, then that information should be communicated in a more reliable manner. Otherwise, your button press will not be recorded. So for that purpose, we may require some form of acknowledgement. Say, for example, if you think of an example of an elevator, you go into an elevator and you press a button, normally that button would light up. So then you have given a user input. That user input was communicated to the controller, and then the controller has acknowledged the receiving of that information, then the button would light up. So if that is the scenario that we have, then we can sort of reliably say that information was communicated. If that button doesn't light up, then we would say, okay, something went wrong there. So the main sort of issue or concern here is the delay, and if there could be any delays in the case of overloading. For example, if many people are suddenly sending some event-based messages, then what would happen? Would that overload the system? Would that reliably communicate all of the messages? So that is a challenge that we would have to overcome or manage when we are working with event-based systems. But the main advantage, or the reason we would go for event-based systems, is that they would be fairly efficient in terms of the use of network resources. But with state-based systems, here the advantage is messages are sent on a predefined manner on a regular interval. So if a message is lost, it would be okay. So in event-based, the problem was if the message was lost, it was only sent once, so then that would be a problem. Say if we think about a temperature sensor reading example, here if the temperature sensor reading was sent once and it was missed in the communication, then the next minute there's going to be another sensor reading, and as long as we have fairly reliable communication, then that should be enough. We don't need a very high reliability in terms of communication, because losing a single message may not be a significant problem. But the disadvantage is, because we are going to keep on sending these messages at a fairly regular intervals, then the problem is the communication channel may be inefficiently being used for these messages which don't carry any changes. For example, currently the temperature is 25 degrees Celsius. Then after a minute it is still 25 degrees Celsius, but we would still send a message because it is not based on the change of temperature, but rather it is based on the current temperature, the state. So we would still send messages that may not add a lot of value in terms of new information, but that is how state-based systems would work. And one of the other things is, because state-based systems are going to send information only at certain intervals, any change that may happen between that interval points may be lost. So that is what we would call as the transient data problem. Say, for example, if we think about the example of temperature change, and if we have a temperature sensor that is sending out every 5 minutes, for example, so we would observe the temperature now, and in the next 2 minutes the temperature goes up and then again comes down again back to the same original temperature. That particular change that happened in between will be lost. Say in the case of button presses, for example, unless that button press was recorded, or like it is kept being pressed until that moment of sending that information, it may not be recorded. So that's why we may not use such a method or mechanism for user input type of scenarios, because it may be affected by the transient data problem. So we may go for event-based systems in some of those scenarios and use state-based systems for other type of communication. And one of the other advantages that we would have with state-based systems, particularly with sensory communication, is because we are using using regular intervals, regular message updates. So missing a single message is okay. So we don't also need to have an acknowledgement. We don't need to receive back an acknowledgement saying the message was received. So message is sent, so, and whether it is received or not received is not important. So because there's no acknowledgement is to be received, the infrastructure that is needed or the communication device that is needed doesn't have to be so sophisticated to process acknowledgement. It can just do one-way communication of sending out messages, and that's about it. So that is also an advantage, particularly with low powered, low processing power embedded systems. So they can do very minimal amount of communication of sending out information and then be done with that. So there are certain disadvantages in terms of efficiency and things like that, but there are also advantages in terms of being more tolerant and being able to build with lower resources and things like that. So when we think about communication principles in general, so generally not just with embedded systems, one of the things that we would do is the notion of layered architectures. So breaking the complexity of the communication protocol into multiple layers, with the lowest level layers like the physical layer, for example, will deal with the lowest level signaling communication, and then the higher levels will do more of the information communication. So breaking down the communication protocol activities into different layers. So that is something that we would find a lot in many communication methods. Then when we think about the lowest physical layer communication, there we would again come across, we can think about it in sort of three different ways. We can think about having parallel communication. So that is when we have a set of parallel lines and each of them carrying a bit each in parallel. So depending on how many bits that we can carry, so this would be a 4-bit parallel communication, for example. In the case of serial communication, we will only use a single line essentially for data communication, and we would carry the bits one after the other with a particular timing interval. So we will have a timing interval, and based on that we will send new bits. Then one of the other sort of physical layer communication that we are seeing a lot more commonly used these days is the wireless communication. So there's no physical medium there, but it is still the the lowest physical layer communication that we can have. So these can be things using radio waves, sometimes optical communication like infrared. So, but still, it is any one of those wireless communications. So, when we think about a particular communication standard or communication method that we want to have for our system, for our embedded system, we can think about some of these aspects in terms of what we expect from our communication method. So, whether it is a simplex, duplex, or semi duplex communication, so we'll look at that in a bit. Whether we are using serial or parallel, so that is whether we can send multiple bits at the same time or a single bit, that is serial or parallel. Whether we have to do synchronous or asynchronous communication, and mainly the data throughput. So that is the total amount of data that we can transfer between two nodes within a said period of time. So that is what we mean by data throughput. So these are some of the things that we would look for when we are looking to choose a particular communication method. The idea of simplex, half duplex, and full duplex are fairly straightforward. You may have come across these with data communications and similar modules as well. So, what we get here is with simplex, we only have a single direction of communication. With half duplex, we have both directions, but only one direction can communicate at one time. And with full duplex, we can communicate in both directions at all times. So when we think about embedded systems, we can use any one of these as part of our communication. Say, for example, if we think about a state-based communication, a sensor wants to send out some information to a controller. So if let's take this, if this is a sensor and this is a controller, if they need to send out information using a state-based communication, they are just sending out information periodically. There's no acknowledgement being received, so there's nothing like that. So having a simplex one directional communication is good enough in that situation. Sometimes even when we think about event based and we are sending information and receiving acknowledgements, and if there's no requirement to receive acknowledgements while more information being sent, then we can even have half duplex. So we will send something, we'll receive acknowledgement, then we'll send again. But in most cases, particularly with general computing, the preference goes to full duplex, where we can send and receive information back and forth between both nodes. But particularly with embedded systems, there is an argument to be had that even simplex and half duplex communications may be suitable in certain situations and may even be efficient, cost effective in those situations. Because if we don't need full duplex, then we don't want to use full duplex because it can be a more complex setup compared to having a simplex communication. Then with data transfer, we can categorize them into parallel and serial as we looked at. So within data transfer, we can look at parallel communication or serial communication. And within serial, we have the categorizations of synchronous and asynchronous. We'll look at each of these in a bit more detail now. With parallel communication, the idea is that we can transfer multiple bits. Transferring multiple bits at the same time is the main advantage of having parallel communication. So usually we may find 8-bit, 16-bit, 32-bit. So the number of wires that we are going to have is the number of bits we can transfer. So we would normally talk about these wires that are carrying the bits. But in addition to that, we may sometimes have other wires such as clock signals, power lines, and so on. But we don't normally talk about that when we are counting the number of wires relevant to the data bits. So when we think about the way of communication here, it would be comparatively simple and fairly easy to implement. But the problem is, it would be very much expensive or bulky when we think about using parallel communication over long distances. Because if you want to have 8 bits, then we need to take 8 wires. If you want to have 32 bits, then we need 32 wires. So it may not be an ideal option or an ideal solution for long distance communication, but within controllers, sensors that are closely located, this can have the advantage of being able to communicate much faster in a much simpler communication method. Because all we need is, say, if we are sending 8 bits, we just put the 8 bits in one at each line, and then that is available as the 8 bits at the other end. It's a fairly straightforward approach. So in addition to the data bits, we will need one data bit per, so we can one wire per data bit. But in addition to that, we will have control lines, power lines, and those as well. But the main advantage is high data throughput, particularly in short distances. It's generally high data throughput, but the problem is over long distances it may not be ideal. So typically where we would use parallel communication is when we are communicating within the same circuitry or within the same device. Using parallel communication would be okay. Because we want to keep it short distance, because if we go much longer distance, then we would have issues relevant to electromagnetic interference, charge losses, and things like that. So there could be issues like that. So we would want to minimize the distance of data travel when we are using parallel communication. But the main disadvantage that we would have is that it can be fairly costly and bulky. Say if we want to go from 32-bit to 64-bit, now we need to effectively double the number of wires that we need to use, and it can become pretty bulky to do that. Serial communication, on the other hand, what we have is we would have a single line which would carry a single bit at a time. So what we have here is one bit at a time, and what essentially we only need a single wire, but normally we would have few other wires, control lines, clock lines, and all that. But basically we would need at least one wire to do the data communication. So from a size point of view, this would be significantly smaller and compact than a parallel communication. So that is one of the reasons why we may use these much more commonly when we are building embedded systems than parallel communication. Most of the sensors that we may want to interface with, most of the other control systems, it is fairly common to find serial communication being used than parallel communication. So what we would have to do is we would have to break the information that is being sent out into single bits and communicate one after the other, and we can achieve fairly good data throughput, particularly with long distances, because it is a single wire or few number of wires, so less effect by capacitive interference and so on is pretty less. So we can send out the information through more longer distances. And the main advantage is that they can be fairly cheaper and less bulky. So again, when talking about embedded systems, portable applications and so on, serial communication would be much more suited there. But the disadvantage or the challenge that we would have to face is we would need additional complex logic for the communication protocol, because we would have to break down the message into individual bits before it can be sent through the single wire we have. So whatever the information, we'll have to break that into pieces. Then at the other end, we'll have to compose it back into the original message. The sender will have to decompose and the receiver will have to recompose. In addition to this, we may also sometimes send other control signals and stuff like that. So again, that would lead to more complex protocols, because we'll have to have more protocol level communication separation to identify each bit, identify control signals and the data signals, separate them, decompose and recompose at each end. So the actual communication protocol can be much more complex compared to just using the parallel communication. So there's no breaking down there. We just send each bit on a separate line. With serial communication, we can further break that down into two categories as synchronous serial transfer and asynchronous serial transfer. With synchronous serial transfer, what we have is we will go according to a particular clock. We'll go according to a particular clock signal, and we will keep on sending information according to that clock signal. So the information will be continuously sent according to that. With asynchronous serial transfer, we don't have to continuously send information. So we can send information with certain gaps. So in between, there's no information is being transmitted. But if we go with the asynchronous approach, then we'll have to have some mechanism to indicate the message transfer is starting now and the message transfer is stopping now. So we'll do that with what are called start bit and end bit, and we'll have a certain data size and things like that. So that is what we would do with asynchronous serial transfer. So one of the important things that we will come across, particularly when thinking about embedded system, is that serial communication would be more preferred, or rather the more preferred way of communicating when we are building embedded systems. One of the main reasons is it occupies less space, because many embedded systems may have space limitations and things like that, and using serial communication will have a number of advantages there. And another main advantage is that because we don't have a lot of wires interconnecting these nodes, there's no issue in the form of crosstalk. So there is interference and things like that are not there when we are using serial communication. So even from a cost point of view, again, one of the things that we would try to achieve with many embedded systems is sort of cost efficiency as well. So in that point also, using serial would be much cheaper option than having parallel, particularly when the connections needs to happen over long distances. So for this reason, it would be fairly common for us to find serial interfaces than parallel interfaces in many control systems, many sensors and related devices. It would be fairly commonplace to find serial interfaces than parallel interfaces. So, when we think about serial communication protocols, there are again a variety of serial communication protocols. We are not going to go into details of any of these protocols. That is not the main intention of this particular lesson. But you can find a lot of resources if you want to study about any of these communication protocols. How they work, the underlying protocol architecture and all. You can find resources and study about them. There may actually be an assignment given on the communication protocols later on. I will share the information on that on Google Classroom later. So, when particularly thinking about embedded systems, we would come across communication serial protocols such as UART, SPI, I2C, CAN or CAN bus or control area network. USB is a serial bus, universal serial bus. It's a serial communication bus. Mainly used in general purpose computing, but can also be used in embedded system design. And one of the interesting protocols that you may find is what is called a one wire protocol. It is essentially a way of using serial communication with just one wire. Even many of the other serial communication protocols don't need a lot of wires. So I would highly advise you all to have a further sort of look at these with online resources. Okay, that's a repetition of a slide. Actually, I guess some slides are repeating. Okay. Then another thing that we can look at, particularly with significantly higher adoption with embedded systems these days, is wireless communication. Because many sort of embedded system applications would benefit from not having to connect to a physical communication network, because the way that they will be deployed, where they will be deployed, it would be much easier if they can communicate through wireless communication. So instead of having wires running from sensor to controller, it would be ideal if they can communicate through a wireless communication protocol. It would be much more beneficial. One of the earlier versions of wireless communication that you may find a lot in even a lot of household appliances is infrared based communication. So if you think about your television remote controller and things like that, or even air conditioners and stuff like that also use IR remotes. So they basically communicate using infrared wireless communication, but through infrared. But the one of the main advantages of why infrared communication is used in many of these devices, it is pretty cheap. You only need a diode that can emit infrared light. Then you pulse that light to indicate the bits that you are communicating, and then you are done with that. So it's not a very complex things to do. So it is very cheap, and we will find this in many places. But the the main disadvantage is that we need line of sight and a limited range, because it can only travel as far as that infrared light can travel, and we need to be in line of sight for that communication to work. So in certain embedded systems environments this can be used, but not a suitable option for many other scenarios. What would be more suited is wireless communication that is based on radio signals, radio waves. So electromagnetic waves in the radio spectrum. So what we need is antennas and receivers and do some data transmission. But the main advantage here is we don't need line of sight, even though there could be limitations in terms of the penetration through barriers and things like that. But depending on the power of the transmitter, we can travel to a larger distance. So in many sort of embedded systems applications, it may be ideal, if you want to use wireless communication, to go with a radio frequency option than going with infrared options. So now if we look at the type of communication protocols that we can have in the area of embedded systems, it's going to be pretty sort of complex setup. Not complex, these protocols are complex, but also a lot of different protocols, and some are sort of application specific protocols, like there are certain protocols that are used in automotive industry. So you can have like a network within an automotive device, so all the controllers, sensors and things are connected through that device. We can have building automation specific networks. We can have other things like military and other applications. Then there are certain standards like BACnet for buildings, SafeNet for again certain military and like that type of applications. Then we have a lot of protocol implementations like control area networks, Ethernet ArcNets, sort of various IEEE standards that are there for different protocols. Then we can also categorize some of these communication protocols based on the way that they are going to use the medium. So the type of communication, things like token ring or TDM, token bus, and things like that. So what I essentially want you to take away from this is not that there's a lot of them, but that because there's a lot of these communication protocols, we may choose any one of these, but depending on what we are trying to build as our embedded system. Say, for example, if our embedded system is relevant to the automotive domain, then we may choose some of the protocols that is relevant to that. If our if our product, our embedded system is relevant to buildings, then we may choose something that is relevant to that domain. So we'll have to think about where the application domain of the embedded systems to choose these protocols. But the specific details of these protocols, we are not going to go into detailed discussion of that in this course, because it is not very relevant for what we are trying to do here. And also these protocols change, so if you are building something, you would be able to choose the best one that is available at that point in time by doing a bit of research. So that is what I want you all to do as well. Just for example, we look at some of the common protocols that we may find in embedded systems. For the use with embedded systems, we have a protocol called I2C, and one of the main points is it is a 2-wire serial bus. It is only, so you need only 2 wires for communication. So it has a lot of advantages because of that. And it has a fairly okay data rate. It's not a very high data rate, but it is a fairly okay data rate depending on how we are using them. And this is mainly used to interface sort of various devices, microcontrollers, timers, clocks, and things like that. I2C can be used. So what we will have is we will have the I2 bus, and to the I2 bus we can connect the various devices like the microcontrollers, EPROMs, sensors, various sensors, displays, and things. So all these devices as part of our embedded system, all the components of our embedded system can be connected to the same communication bus, and then we can communicate using the shared I2C bus. An interesting option that we may find is what is called in embedded systems, particularly when we think about automotive industry, automotive applications, is what is called CAN, or control area networks. This was particularly developed for cars, but it can also be used in other situations, other systems these days. Things like industrial controllers, elevators, production lines, things like that. But one of the main aspects of this CAN protocol is that it is designed for real-time applications. So we have looked at these real-time requirements in systems when we need to meet the deadlines. So things like automotive applications or things like elevators and production lines, they will have these real-time requirements. So CAN is more suited for that type of application. Then USB is actually one of the interesting protocols that we may find because it is a common standard that is pretty commonly used in general purpose computing. So we find a lot of general purpose computing related peripherals having USB as the interface. But it is also fairly common that we may find some of these devices being used in embedded systems applications, and we could use USB as an interface, and also we can use USB for interconnecting sensors and other things in a purely embedded systems manner as well, but also as an interconnect mechanism. So USB is also something that we may come across time to time in embedded system environment. There are certain parallel communication protocols, but they are not very much used in embedded system applications, at least in the sense of connecting to embedded system specific components. These may be there internal to the main computational aspects of embedded systems, the main microcontrollers, main microprocessors. They may use some of these parallel protocols such as PCI buses, PCIe, and other variants of PCI. They may use that, but in sort of the main embedded system specific communication, parallel communication is not the more common method to use. But one of the places where we may find parallel communication with embedded systems is what is called the ARM bus. When we are using ARM microcontrollers and ARM processors, ARM has what is called the ARM bus, and there are many, can't say many, but at least a good number of other systems that support the ARM bus, and we may be able to interface these using such a parallel protocol. But still, not one of the most commonly used communication protocols in the embedded domain. Then with with wireless, again, we can have a number of wireless communication protocols, things like infrared for infrared communication. But as I said, infrared is not that suited for many applications, so may not be commonly used. But if we need, we can use that. But Bluetooth has become a fairly common standard for embedded systems wireless communication because it is pretty low cost and it can travel a fairly good distance, and the newer variants of Bluetooth have a lot of advantages in terms of power saving mode and things like that. So, and we can have Bluetooth sort of sensory networks, sort of interconnected Bluetooth networks and things like that. So Bluetooth is a fairly common standard to be used in embedded system environments. Then wireless LAN, so Wi-Fi, is also fairly commonly used in embedded systems, but the disadvantage with that is they are fairly complex protocols. They are not that simpler protocols, so you may need additional hardware and additional capabilities, processing capabilities to manage the protocol overhead, but they can be used as well. So that's all that we have to discuss in terms of communication protocols for embedded systems. Are there any questions? Are there any questions on things that we have discussed today or anything else? And as I said, we will have a short assignment on possibly I'll let you know what will happen through Google Classroom. So if there are no other questions, we may conclude for the day. And thanks for joining, and see you next time.